Okay, so yeah, welcome to the chemical live session of the NPTEL course, Chemical Process Intensification. And so this is the second live session for the second week. And my name is Mohammad Anzar Hussain, and I'm a PhD student in Department of Chemical Engineering in IIT Guwahati, and I'll be taking the second live session. So, in the current week, what was discussed, the things that were discussed were how to basically intensify or form process intensification in multi-phase flow systems. So, yeah, so today we will be going through that. So, what are multi-phase flow systems? So, before performing process intensification for the multi-phase flow system, let us first discuss what are the multi-phase flow systems. So the multi-phase flow systems are the continuous flow systems consisting of materials with two or more thermodynamic phases. So those are called as the those are called as the multi-phase flow systems. So here note down that okay, continuous flow system, it is not that okay you just put a sessile drop or a stationary drop and say it a multi-phase system, multi-phase flow system. So yeah, that will be a multi-phase system. Basically if you put a drop on a solid substrate, so what will happen is a three-phase system: the solid substrate and the liquid droplet in the surrounding air fluid. So that is a multi-phase system, three-phase system, but it is not a multi-phase flow system. So the point to be noted here is continuous flow system. So any sort of a flowing system, and that consists of material with two or more thermodynamic phases. Now the key here is thermodynamic phases. Now how would you define a phase? Now the phase can be defined that okay, the different phases may either be made up of same chemical component or several different chemical components. So for example, let us say that you are in a channel, in a circular cross-sectional channel, there is also air and water, two-phase system is flowing. So the water is also flowing, and in between that there are some air bubbles is also flowing. So that becomes a two-phase system. That okay, gas liquid system. So or let me go into a much more simpler example that okay, you are boiling, you are taking some water in a glass and putting it out in the sun. So what will happen is evaporation will happen. So the water vapor, so water will turn into water vapor. So here the chemical component, the basic chemical component here is H2O. So that water just changes its phase. So from liquid phase, after getting some thermal energy, after getting some heat, it changes into water vapor, into gaseous phase. So the chemical component remains same. So it is that same chemical component H2O, but in two different phases: in gaseous phase as water vapor, and in liquid phase as simply water, liquid water. Now that same different in another example, it can be given as that that two different phases may be made up of different chemical components. Now here comes the example of oil and water. So you take some vegetable oil and you take some water, and you put both of them in a container, in glass, in your tumbler. So what will happen is whosoever has much higher density will settle down. In this case, generally water settles down and the oil will float at the top. So in general cases, so that's how you can say that okay, both of them are in liquid phase, but they have different chemical component. The oil may be made up of different complex hydrocarbons, and the water is made up of H2O. So yeah, so that is the saying, that is what it meant to say, that okay, with two or more thermodynamic phases, and those thermodynamic phases, different thermodynamic phases, may either be made up of same chemical component or several different chemical components. Now we can classify this multi-phase flow system into different flow systems based upon how many phases are involved and what type of phases involved. So to us, to the general public, the phases which we can easily see in our lives, in our real life, daily lives, is there are three phases. So gaseous phase, liquid phase, and solid phase. So there are other phases of states of matter also. Other phases like you can say plasma and all. So or when you go into the supercritical stage, after beyond supercritical temperature, you might see that okay, that liquid and gas both merge. So neglecting those extreme scenarios and exotic states of matter, to the common public, or not so common, but yeah, what is available in the real life, mostly available in the real life is gas, liquid, and solid states of matter. So yeah. So for the simple two-phase flow system, so the multi-phase now can be two-phase system, three-phase system, four-phase systems. So, but the simplest multi-phase flow system, that in the definition you can see that okay, continuous flow system consisting of materials with two or more. So the simplest can be two-phase system where the two phases are involved. So those type of systems, one of the simplest multi-phase flow systems can be gas liquid flow system, gas solid flow system, liquid solid flow system. So these are the three types of two-phase flow systems. So the prominent examples of the gas liquid flow system where it is, one second, okay, sorry, yeah, so the examples of the unit operations or the chemical equipments that uses the gas liquid flows, or the instruments that use gas liquid flows are bubbly flow towers and separated flows and gas droplet flows. And for the gas solid flows, the common examples are gas particle flows and pneumatic transport and fluidized bed reactor. And for the liquid solid flows, some of the examples are slurry flows and hydro transport and sediment transport. So these are the one of the simplest flow cases. And then comes the much more complex flow system like three-phase flow system and four-phase flow system. And some of the examples for the three-phase flow systems are bubbles in a slurry flow and droplets or particles in gaseous flow systems. Now the multi-phase flow system, apart from categorizing them based on the how many and what types of states of matter are involved, you can also classify the multi-phase flow system, or especially the simplest two-phase flow system, into further. Hello. Hello. Hello, Prashanthi. Hello. Am I audible? Yeah. So, anyways. So the two-phase flow system, like for example the gas liquid flow system or the liquid flow system. So apart from the gas liquid and gas solid and liquid solid flow system, there can be another flow phase system like liquid flow system, like oil and water flow system. So where the both of the where the two of the different phases are in the liquid state, but they have different chemical composition. So yeah, that liquid flow system. Now these liquid flow system and gas liquid flow system can be further divided into can be further categorized into two different flow system, two phase flow system, that is dispersed flow system and segregated flow system. So here the diagram shows the clear difference between them, that okay, that for dispersed flow system, what will happen is there will be some micro bubbles, and not generally micro bubbles, but a lot of bubbles will be involved. So there you cannot clearly distinguish a big interface. So no doubt physically there will be an interface between the gas bubble and the liquid bulk, but those bubbles will be a lot in number, so you cannot basically track individual bubble. It will be very difficult to track. So those type of flow systems can be categorized as dispersed flow system. And the segregated flow system, here you can see that okay, gas is at the top and the liquid is at the bottom, and there is a very clear and sharp interface between the two phase system, clear, big and sharp interface. So here you can classify the flow system as segregated flow system. So the dispersed flow system where you cannot classify the flow into where you cannot clearly distinguish a big interface. And in the segregated flow you can see, so one of the example of the segregated flow system is the stratified flow. So where the gravity acts where the gravitational force is a dominant force. So what happens is, for example, if the liquid has so obviously liquid will have a higher density than the gaseous phase. So what will happen is, so if the gravitational force dominates in such flow cases, so the heavier or the higher density fluid will settle down and separate itself from the top flowing the lighter or the less denser fluid. So this is called as the stratification of flow, and this is actually the cause behind the segregated flow system. So yeah, now the gas liquid flow system, so let us discuss individually about discuss some systems on an individual basis. So for the gas liquid flow system, if the gas is so here in I forgot to discuss one thing, that okay, in the dispersed flow system, the bulk media in which the gaseous phase will be dissolved or the dispersed, the bulk media is termed as the continuous phase or the carrier phase, and the media which is so the gaseous phase which will be generated as bubbles, small bubbles in many in number. So this will be called as the dispersed phase. So kind of it has its own self-explanatory definition, that okay, the phase which is getting dispersed inside the carrier phase or the continuous phase is called as the dispersed phase. Now generally in the gas liquid flow system, what happens is gas is used as the dispersed phase and liquid is used as the continuous phase. Now what are some of the examples of the gas liquid flow system? I mean, if you would have gone through the lectures, the Professor Majumder sir has discussed that a few examples for the gas liquid flow system, like absorption of gas in liquid to remove it from the gaseous mixture. So what will happen is, so in the scrub towers, what happens is you want to absorb certain gas from the gaseous phase, certain chemical species from the gaseous phase by using a liquid solvent. So for example, in carbon capture or CO2 sequestration, carbon sequestration, what happens is you want to capture the carbon dioxide which is present in the air by using some liquid solvent which has much higher affinity for carbon dioxide than the air itself. So what happens is you try to make the contact between the air and the liquid solvent, such as the monoethylamine, which has a very high affinity for carbon dioxide. So what happens is then the carbon dioxide from the air slowly gets absorbed into the solvent, MEA solvent. So this is one of the examples for the gas liquid flow system, the example of absorption of gas in liquid phase to remove it from the gaseous mixture. So yeah, like example of removal of CO2 or carbon dioxide or nitrous oxide or hydrogen sulfide from the polluted air into a given liquid solvent. Another example is ozonation of arsenic or ammonia or dye in water treatment. So what happens in the water treatment plants is you will have arsenic present as pollutant, or ammonia will be present, or certain dyes will be present in the water treatment. So you can perform the ozonation in the water treatment to basically remove the presence of arsenic or ammonia. So what will happen is the ammonia will get ozonated. So another example is the application of gas liquid chromatography for the analysis of liquid petroleum fractions. So you can also analyze the liquid petroleum fraction. So the liquid, the petrol, the crude oil will contain lots of different hydrocarbon species, chemical species, and you can perform the gas liquid chromatography. So what happens is in the gas liquid chromatography is gas is getting contacted with the liquid which is under the study, and there the species which are the interested in which the person or the investigator is interested, it will also get absorbed in the gaseous phase, which will then be used to perform the chromatographic study to identify the species concentration. And another application is gas liquid reactions, such as the industrial gases like oxygen, hydrogen, carbon monoxide and carbon dioxide are widely used for the synthetic processes in the chemical industry. So yeah, the gaseous processes, industrial gases like oxygen and hydrogen. So the oxygen is widely used to perform the combustion reaction and the oxygenation, basically to basically form some stable compounds of a few elements. So yeah, that is also that is a great example of gas liquid flow system. Now coming to the liquid gas system. So here what happens is so we discussed about the gas liquid flow system. Now what if the liquid gas system is used? So here in this case what happens is, so basically we reverse it. The liquid is used as the discrete fluid and the gas is used as the continuous fluid. So there will be the bulk media would be made up of gaseous phase, and there will be small micro droplets of the liquid phase present in the gaseous phase. So this is the scenario of the liquid gas system. So in the liquid gas system, the liquid is used as the discrete fluid and the gas is used as the continuous fluid. Now so few examples of the liquid gas system are the spray column, where the liquid is sprayed in the gaseous medium for the absorption of gas. And so now the spray towers can be very effective in the spray towers can be very effective in removing pollutants if the pollutants are highly soluble in the liquid. And in another example is the production of the superphosphate used in manufacturing fertilizer. So the hydrogen fluoride and the silicon fluoride gases are vented from various points in the processes. So another example are again the spray towers can also be used for the odor removal in bone meal and tallow manufacturing industries by scrubbing the exhaust gas with the solution of potassium permanganate. So yeah, that is how you can perform the odor removal. And now coming to the gas solid system. So in this scenario, what happens is the solids are suspended in gas. So gas is again here the continuous phase. Now the solids are suspended in the gaseous phase. So for such processes, there are basically broader kind, that okay, for the physical processes where there is no chemical reaction is happening. So what happens is, a few examples are drying of particles, that okay, you dry the particles using, so like you will have some solid particles, but if you they have absorbed some moistures, and if you want to dry them, so you will make the hot gas pass through the entire batch of the particles, so that the humidity can be the gas phase can carry the water vapor that may evaporate go through the gaseous phase. So that may lead to the drying of the particles. Now, another example of the physical processes that uses a gas solid system is coating of surfaces and granulation, where the particles are grown. So the granulation process is basically the growing of particles, and the heat treatment or like annealing and quenching, so you can use that. So and gas solid system, one of the example, and filtration, blending and classification. Now, as for the gas solid reactive system, so these were some of the physical systems where there was no involvement of the chemical reactions. So but now for the systems, for the gas solid system where the reaction is also happening, chemical reaction is also happening, is where the examples like roasting of ores, combustion and incineration, gasification, coking and pyrolysis and carbonization, calcination of the limestone, phosphate, aluminum hydroxide, or fluid coking, examples like fluid coking, etc. Now coming to the example of the liquid systems. So here the liquids are used both as discrete and continuous fluid. So here one liquid phase can act as the continuous phase, and another liquid phase can act as the continuous phase. Now the example of such systems can be like that, okay, use of flow of emulsion of oil and water in the pipelines. So the emulsion of oil and water inside the pipeline is a great example of the liquid system. So oil and water do not mix, so instead what they make is an emulsion. So the oil droplets or the oil globules will be suspended in the water if the water is used as the continuous phase and oil is used as the dispersed phase. So such type of mixtures are called as the emulsions. And another example of the liquid system would be that, okay, using of different types of contractors like pegged columns, pulsed column and stir tank reactors in various applications. So yeah, similarly extraction of organic contaminants from the wastewater can be a very good example of the liquid systems. Now coming to the liquid solid systems, so here what happens is the solid particles is dispersed in liquid. So similarly in the gas solid system where the solids are suspended in the continuous gaseous phase, here the solids are suspended in the liquid phase. So the solid particles are here as act as the dispersed phase. Now some examples of the liquid solid system would involve the hydraulic conveying of the solid materials, and slurry flows over a wide spectrum of applications that range from the transport of coals and ores to the flow of mud. And another example would be the crystallization of solids that are suspended in the liquid. So solids like you can grow the crystals, so you might have seen the growth of the copper crystals copper sulfate crystals in the copper sulfate solution. But yeah, so that is an example of liquid solid system. So the crystals of the copper sulfate are the solid here, and the liquid here is the copper sulfate solution, aqueous solution of the copper sulfate. So yeah, that was the example of the crystallization solids suspended in liquid. Another example is the flow of liquid through a solid, so like a porous media flow, so where the liquid is the bulk. So yeah, now we discussed all the two-phase system. Now what about the three-phase system? But for the three-phase system, hello. Now the examples of three-phase system. So yeah, the three-phase system can be further classified into gas, liquid, solid system, gas, liquid, liquid systems, and solid liquid liquid systems. So I will just briefly go over discuss each example of each system, examples of each system. So gas, liquid, solid systems. The examples, like in the mineral industry, fine solids are separated by the flotation technique in the column. So you might be knowing about the froth flotation. So where you try to extract the finer coal particles using the froth. So there will be you will be blowing gas from you will be sending gas through the aerator in the bottom of the column, and then there will be a stirrer or a mixer that will be generating the foam from the liquid. So that foam or froth will be carrying the dispersed solid particles over them. So yeah, that flotation process is an example of gas, liquid, solid systems. And other applications would include the fluid bed catalytic cracking and hydroprocessing, and a few other biochemical processes. Now the gas liquid liquid systems, now coming to the gas liquid liquid system, it is a very common system, gas liquid liquid systems. So like oil, water and natural gas is a very common system. So oil is there and water is there and natural gas is there. So what happens in the mines of the oil mines, the natural gas will sit on the top, and then the oil will sit, and then in the bottom the water will sit. So based upon the density, so sometimes water may be up on the top, but yeah, so that is a very common example that natural gas is also found where the oil mines are there. So while mining for oil, you might also the industry people also find the natural gas. So oil, water and natural gas is a very common gas liquid liquid system. Now another example of a gas liquid liquid system would be evaporation of the immiscible liquid mixture. So there will be, for example, if the water is getting evaporated and oil is also present in between that. So the oil makes a different phase and water makes a different phase. But if you have not reached the temperature, evaporation temperature where the oil starts to evaporate or the oil starts to smoke, so basically the water will get evaporated first and the oil will stay there. So yeah, that is the reason why, because the water boils faster or evaporates faster than the oil. So we use oil for cooking rather than water. So yeah, the water may evaporate faster and in the lower temperature than the oil. So while evaporating, the gaseous phase would be consisting of water vapor. So this is a clear example of the three-phase gas liquid liquid system. And another example of the three-phase system would be solid liquid liquid system. So the examples are that in the pipeline, if sand is mixed with oil and water, so three-phase flow becomes. So when the oil is extracted, so it is mixed with a lot of dirt particles, sand particles, and also it has been it makes an emulsion with water. It makes an emulsion with water. The mixture consists of the oil, crude oil, and water, and with a mixture of dirt particles and or sand. So that makes a great example for the solid liquid system. So here the liquids are all crude oil and water, and the solid are the suspended dust particle or sand. Now coming to the examples of the four-phase system. Now in the four-phase system, one of the prominent example is the liquid gas solid system. So such liquid gas solid system, one of the example is the freeze desalination. In freeze desalination process, what happens is when the butane liquid is added to the saline water, so this results in the formation of icicles. So this is utilized in the freeze desalination process, where the butane is one of the liquid and saline water or the brine water is another liquid phase. And then what happens is the formation of icicles, where the ice will also sublimate and also basically crystallize form, so that becomes a solid. So yeah, that is one great example. And another case system is the mixture of butane liquid, water, ice, and the butane vapor. So this is another example of the four-phase system. Now let us discuss some mechanism based on the multi-phase flow system. So we have discussed what are the different multi-phase, some examples of the different multi-phase flow systems. We have first characterized that, okay, what is a multi-phase flow system? We have defined it. Then we have classified that, okay, what are the different multi-phase flow system available, and based on that we have discussed a few examples of the multi-phase flow systems. Now what are the mechanism based on specific multi-phase flow system? So for in the example of the slurry bubble column systems, multi-phase systems, what happens is the mechanism what is exploited is the creation of interfacial area between the phases to enhance heat and mass transfer. So that is the idea behind the operation of the multi-phase slurry bubble column system. And in case of the multi-phase fluidized bed reactor systems, so the mechanism that is exploited or is used is the gas solid flow system, so which is used for the better heat and mass transfer operation. And rotating disc packed bed systems, multi-phase system used, they generally perform for the so rotating disc system that we have discussed in the previous session also, that okay, rotating on the centrifugal distillation tower, but what about if they are if you involve a packed bed also? So that what results in a better mass transfer of weld, mixed liquid and gas phases, and very high interfacial surface area you would get, and in a counter current fashion. So yeah, so your liquid would be flowing on the other side, and your packed bed would be flowing on the other side. So yeah, you can also make it in a counter current fashion. So you would get a very better mass transfer and liquid mixing also. Now, as in the case of the for the case of compact heat exchanger, by reducing the channel size or using a micro channel, you might generate a lot of high powers as compared to the conventional heat exchanger. And in the case of foam heat exchanger, so basically you perform the surface enhancement by metal coated polymer foam for micro power generation. Now in the case of the inverse flow reactor, the mechanism that is used based on the multi-phase flow system is to increase the residence time and better phase mixing. Now as for the membrane distillation, the transport mechanisms are Knudsen diffusion and Poiseuille flow and molecular diffusion. The thermal boundary layer is considered to be the mass transfer limiting factor. So that is for the membrane distillation. But in the case of the liquid membrane, so the liquid membrane offer rates several order of magnitude higher than the solid membrane. So instead of the solid membrane, the liquid membrane they offer transport rates several higher order of magnitude than the solid membranes, because the diffusion is faster in liquids than in solids. So yeah, that is the reason why you can use the liquid membrane also for the performing process intensification. Now in the previous session, also in the previous week, what the topics were discussed were that the process intensification can also be done by combining two different processes. So like if two different process stages, like there is a stage of reaction stage, and then there is, after performing the reaction, you will get the product, so you will get the yield, and that yield would contain also the product in combination of the byproduct. So then comes the separation stage, where you will separate the product from the byproduct stage. So what about if you combine both the reaction and the separation stages together to basically make a reactive separation stage? So now the reactive separation for the different phases can exploit, basically they are given different names, the different processes, based upon the different multi-phase flow systems used in the reactive separation systems. So the techniques are named different, but yeah, the idea is same, that you combine the reaction and separation stage together, but they have been labeled into different systems based upon what types of phases are used. So when the gas vapor system, in the gas solid system, the reactive separation stage can also be called as the reactive adsorption stage. So what happens is the gas will get adsorbed. First the gas and solid will perform, there will be a reaction stage also, but then the gaseous products will also get adsorbed into the solid substrates. So such type of gas solid systems where the reactive separation is going on can be labeled as reactive adsorption. Now similarly, in the liquid solid systems where the reactive separation is happening, such stages can be called as the reactive chromatography stages, reactive chromatography processes. And now similarly, now in the case of the gas liquid system where the reactive separation is happening, such type of systems can be called as reactive absorption stages, processes. So in the case of the gas solid reactive separation, they were called as the reactive adsorption, but in the case of gas liquid reactive separation process, they are called as reactive absorption. And now the reactive separation in the case of liquid multi-phase system, two-phase system, such reactive separation processes are called as the reactive extraction processes. Now the reactive separation units may also be treated as a kind of multifunctional reactor in which the functionalities of several processes are combined to generate a new reactor concept. So yeah, that is the crux behind the combining or performing process intensification using reactive separation technique. Now out of all of these, the three most important example of reactive separation processes are reactive distillation, reactive absorption, and reactive extraction. So these are the three very important reactive separation processes. And now what are the common features of the reactive absorption, reactive distillation, and reactive extraction processes? The common features of the three of them is are they involve at least one liquid phase. That is common, that okay, in the reactive absorption you basically do perform the reactive separation using gas liquid multiphase system, and in the reactive distillation you use the gas liquid system, and in the reactive extraction you use liquid liquid system. So basically in all of these three systems you involve at least one liquid phase. And another common feature of these three are that the properties of the liquid state become significant. That okay, here the properties of one of the liquid state is highly significant, that okay, one is getting extracted. And the another common feature of the reactive absorption, distillation and reactive extraction is that they occur in moving systems. Thus the hydrodynamics plays a very important role. So all of these three systems, reactive absorption, reactive distillation and reactive extraction, they all happen in a continuous fashion. So the hydrodynamics of the flow becomes a very important part of the study. Now these processes are based on the contact of at least two phases, and therefore the interfacial transport phenomena have to be very highly considered. So because these processes are based on the contact of at least two phases, so interfacial phenomena becomes very significant, like interfacial mass transfer, interfacial heat transfer. Sorry. So it is in research today also it is a very hot topic, that okay, to basically perform or to study the interfacial mass transfer at different contacting level of the gas liquid or the liquid liquid systems or continuous flow systems. Now the multi-component interactions of mixture components, a tricky interplay of mass transport and chemical reaction and complex process chemistry and thermodynamics. So yeah, this interfacial the presence of interface makes everything a very complex system. So for an example, in the mass transfer, what happens is, in case of heat transfer, whenever there is some presence of an interface, so what happens is the boundary condition that is applicable in such cases at the interfaces are that the continuity of fluxes. That for example, if the flow is happening in the x direction, the heat transfer is happening in one dimension, x direction, so the dt by dx must equal to the dt by dx at the interface. So yeah, the fluxes should be equal. But in case of mass transfer, whenever there is an interface, what happens is you must also include another type of boundary condition, that is the dynamic equilibrium condition, or one of the idealized or one of the most commonly used dynamic equilibrium condition at the for the interfacial mass transfer is Henry's law and Raoult's law. So yeah. And yeah, if you involve multi-component also, then it becomes a lot of difficult situation to analyze and to perform studies. So that is why it is currently a very hot topic. And now coming to these three, now one of the most important out of these three, reactive absorption, reactive distillation, reactive extraction, or I should say that one of the most hot topic or extensively discussed one out of these three is the reactive distillation process. So let me just discuss briefly what is the reactive distillation. Now, yeah, the reactive distillation. So here in the reactive distillation, complex interaction between the chemical reaction and separation happens. So here we combine the reaction and separation stages together. So that is why it is called as the reactive distillation, and lots of complex interactions are there. And the performance is the performance of the reactive distillation is influenced by the size and location of the reactive and non-reactive column section. Not only that, the reflux ratio, feed location or throughput also plays a very important role behind the performance of the reactive distillation unit. Now, some of the example, one of the very common example of the reactive distillation is the esterification and hydrolysis reaction, which are catalyzed by the acidic ion exchange resins like amberlist 15. And the reactive distillation, the reaction and distillation take place within the same zone of a distillation column. So yeah, as discussed, that reaction and separation stages are combined together. So the reaction and distillation takes place within the same zone of a distillation column, and the reactants are converted into products with the simultaneous separation of the products and the recycling of the unused reactants. Now, among the suitable reactive distillation processes are like esterification, nitration, esterification, transesterification, condensation, and alkylation. Now, this operation, the reactive distillation operation, provides a promising process alternative to the traditional sequential operation. But the potential advantages of the reactive distillation are that new and less expensive products, higher efficiency because of the overcoming of the thermodynamic and kinetic limitations, better selectivity due to the suppressing of the undesired reactions, avoiding of hot spots, higher raw material conversion, savings due to the smaller equipment, and less environmental pollutions are among the some of the few potential advantages of the reactive distillation. Now, after the discussing the reactive distillation, we move on to the performing process intensification in a multi-phase microreactor. So now we are slowly getting into the multi-phase microfluidics part. So that now the advantage of the microreactor is their potential for rapid heat and mass transfer. The enhancement of the process of the transfer processes is related to the decrease in the diffusion path on the micro scale. Now, what happens in the microreactor is as the size decreases, the net available surface area increases. Now, for the heat and mass transfer, if you see the Fourier's law and the Fick's law, they both contain that the mass flux is directly proportional to the net available surface area, specific surface area that is available for the heat or mass transfer. So you multiply the concentration gradient or the temperature gradient, which are the driving force, with the net available surface area for the mass transfer or heat transfer to happen. Now, as the size decreases of the reactors, so basically micro reactors. So the in the previous session also I have defined what is a micro reactor. So let me define it again. That micro. So yeah, let me first define what is a micro reactor. So the reactors that are having the handling volume in the range of microliters, or their smallest dimension being less than or equal to 1000 microns or 1 mm, can be called as microreactor. But the microreactor, because of their small size, they are able to provide very high surface area to volume ratio. Now, so because of the increased surface area to volume ratio, their potential for providing rapid heat and mass transfer is very high. Now, another thing is that the enhancement of the transport processes is related to the decrease of the diffusion path on the micro scale. Now, because of the small scale, small characteristic dimension, the diffusion path, the path where the concentration the species has to diffuse, is very, very small. So that's why, because of the very small diffusion path, the transfer, the rate is very fast, and thus the transport process gets enhanced significantly. Now, for the fast multi-phase reactions, the rate and selectivity of the chemical process can be greatly influenced by the transport of the reagents within and across the phases. Now, microreactors are developed for a variety of different purposes, specifically for applications that require, a high heat and mass transfer coefficient and well-defined flow patterns. The spectrum of applications for the process intensification using micro reactors include gas and liquid flow, as well as gas liquid or liquid liquid multi-phase flow system. So you might notice that here we are not mentioning the involvement of solid particles as of yet, because what generally happens is, due to the very small constricted size, what may happen is, if there is a particle, the particles generally tend to coagulate, and coagulated particles may then basically jam the microreactor, so then the flow will not happen. So typically what the applications include for the applications that are used that are performed in the microreactor environment are gas liquid or liquid liquid multi-phase flow systems only. That is, very rarely solids are used here. Now, why intensification from macro to micro reactor? So when you compare both the processes, the microreactor with those, when you compare both systems, the microreactor with the conventional system, the general differences can be listed as that, okay, the flow in microstructure is predominantly laminar. So microstructure, so you know that, okay, Reynolds number is defined by the rho Vd by mu. So here the rho is the density, V is the velocity, and D is the characteristic diameter, and divided by the dynamic viscosity mu. So in the Reynolds number, the diameter, if it gets from macro to micro, so if the range of the numbers that are used for the diameter characteristic dimension in the Reynolds number is in the range of micrometers, so what would happen is you will get Reynolds number very, very low. And as in the general chemical engineering, in the basic chemical engineering, we know that for a circular cross-sectional pipe flow, the laminar flow exists for the Reynolds number below 1000. So, and the transition basically remains below 2300. So at such low Reynolds number flow, it is bound to happen that flow inside microstructure will be predominantly laminar. So in contrast to the turbulent flow pattern on the macro scale. So if you have a pipe of very big dimension, you will obviously notice that the flow inside such pipe would be turbulent in nature instead of laminar. Another difference between the macro to micro reactors are that the diffusion path for the heat and mass transfer are very small, making micro reactors an ideal candidate for the heat and mass transfer limited reaction. So the diffusion path for the heat and mass transfer are very small. So in the case of micro reactor, so it is a very ideal environment to perform heat or mass transfer limited reaction. So the reaction kinetics can be limited to either just to the reaction kinetics if the reaction rate is quite slow. But other than that, if the reaction kinetics is mass transfer limited or heat transfer limited, it is better to perform such reactions in micro reactor environments. Now, why intensification from macro to micro? Another significant difference between the micro and micro reactor environments are the surface area to volume ratio, what I have discussed just now. The surface area to volume ratio of the microstructure is very high. The surface effects are likely to dominate over the volumetric effects. So surface effects like the surface tension, heat and mass transfer. So heat and mass transfer are heavily surface area dependent phenomena. So if you have in the micro reactor, the surface area to volume ratio is very high, so it is likely that the surface tension phenomena and the heat and mass transfer will be enhanced very significantly. Marangoni effects, which highly depends upon the presence of the gradient of surface tension, will be highly enhanced also, but giving you extra new kind of hydrodynamics. So it is again a very hot topic in research. Now another difference between the macro and micro environment is the share of the solid wall. The share of the solid wall is pretty higher in the micro environment as compared to the macro environment. So a microscopic equipment, same equipment but of microscopic size, will have a very high share of solid wall rather than the macroscopic size of that same equipment. The solid heat transfer plays an important role. So if you have a very high surface, again wall available for a given liquid volume, so heat transfer through the wall would be significantly enhanced in case of microreactors than in the macro reactors. So the solid heat transfer will play a very important role and has to be accounted for. This has to be accounted when designing microreactors. Now, using the silicon microfabrication, so it is possible to construct packed bed microreactors that provide 100-fold or more improvement in mass transfer for gas liquid heterogeneously catalyzed processes such as the hydrogenation of unsaturated carbons. Now, in such silicon lithography fabricated microreactor, these devices, the standard catalyst particles are approximately 50 to 75 picometer diameter, are retained in silicon channel by integrated microfabricated filter unit. 50 to 75 micrometer diameter are retained in the silicon channel by an integrated microfabricated filter unit. A specifically designed gas liquid inlet section with narrow channels provide rapid contact of the gas and liquid reagents. And in order to achieve uniform flow, the pressure drops in the inlet gas and the liquid section exceed to those in the individual reactor channel. Basically, if you perform the bifurcation, so yeah, you will have much more higher pressure drop than in singular channels. Now the so in case of microreactor, the small particles provide the high surface area for improved gas liquid mixing, but they also represent a challenge in terms of pressure drop and fluid distribution among the parallel channels. So these small particles, when they are basically uh, uh, they they will they will result in a very high pressure drop. So, and these pressure drop can be reduced by placing catalyst bed, by replacing the catalyst bed by a microfabricated support structure. So instead of placing individual catalyst particle, the catalyst bed can be replaced with a microfabricated support structure. So in case of microreactor, the microreactor environment provides extreme uniform environment. So this extreme uniformity of the structured packing arrangement provides very high control over the fluid flow, and that greatly enhances the relative to the micro packed beds. And the activity is greatly enhanced if the catalytic component is supported over a porous layer formed by making the silicon posts porous. So those silicon posts can be made porous. The direct fluorination, as an example, serves as an inspiration for the development of flow distribution, allowing controlled scaling of the gas-liquid reaction from a few channels to a large number of channels with uniform flow distribution of a flow regime of plug or liquid segments. So intensification, so these basically comes under the intensification by flow in special geometry of the channel. So in some cases, for example, when the large residence times are desired, comparatively long microchannels have to be integrated into a compact microreaction device, a task that can only be achieved with curved channels. So in the previous class also, what I have just shown you that, okay, utilizing curved channels, you can basically exploit the formation, the secondary vortices, formation of the secondary vortices of the curved flow path, such as the Dean vortices, to intensify the mixing. So that is the same idea here. And in addition to this curved channels, the straight channel can often not suited for the connecting a microflow domain to the external world. The secondary flow, called as the Dean flow, as we have discussed in the previous session also, due to the curved path perpendicular to the main flow direction induced by the inertial forces, is a factor for the process intensification. So the typical flow pattern in curved channel is given by the two counter-rotating vortices separated by the plane of curvature. And the strength of these vortices increases with increasing the Dean number. Now the Dean number is basically defined as the Reynolds number into the square root of the hydraulic diameter divided by the mean radius of the curvature of the channel. So this allows us to discuss that, okay, what about instead of microreactor, micro heat exchanger development. So you have seen the conventional heat exchangers, how big they can be, but what about the micro heat exchanger, the development of micro heat exchangers? So at the identical values of the pumping power and pressure drop, in the literature it can be found out that the zigzag channel outperforms the straight channel by up to a factor of 6. So for the same pumping power and for the same pressure drop, a considerably high heat flux is achieved in curved microchannel. So this is a very interesting result in the view of the design of the micro heat exchangers, where the goal is often to increase the heat flux while limiting the pressure drop. Now that we have discussed the process intensification in multi-phase flow system, now another aspect is that okay, we have discussed that okay, we can combine different so we have first defined I first defined that what is a multi-phase flow system. Then we have classified or characterized what are the different types of flow system, multi-phase flow system available. Then we have extensively discussed over the reactive distillation multi-phase flow system and multi-phase micro reactor systems. Now, if you notice that okay, what is the key behind process intensification in such multi-phase flow system? So the key behind all of this is mixing. How well can you mix those immiscible phases, because the phases are separate, and the goal or the general idea behind each and every process is that you want to absorb or you want to extract or you want to distillate out one of the specific species component in which you are interested, that is available in one phase which is immiscible in the different phase, that may or may not have high affinity for that given interested species of interest. So now the idea is in each of those cases the idea is how you can enhance the mixing. So the heart of the chemical engineering lies in mixing. How well can you mix two immiscible phases, or how well can you establish a contact between two of such immiscible phases to perform the mass transfer or heat transfer, or to perform the to basically start to make the reaction happen. So now the mixing is a very crucial and very basically the heart of the chemical engineering. Now what is mixing? The definition of mixing is the process. Mixing is a process of combining two or more substances to achieve uniform distribution and homogeneity of concentration, temperature, etc. Now mixing is the most crucial operation in chemical engineering. So mixing is the heart of the actually the heart of the chemical engineering. How well can you perform mixing? So you pick any equipment, any process unit operation. So the idea is that okay, how can you intensify the mixing if the reaction is happening in them? Now obviously in separation processes you do not want them to get mixed. So it depends upon the context, that okay, if you want a reaction to happen where you want two immiscible phases to get into contact, you need to perform mixing. The key aspects of mixing operation include homogenization, mass transfer, heat transfer, reaction kinetics, and scale up. So the key aspects of the mixing is that okay, how well can you homogenize, or basically the two immiscible phases can be classified as a heterogeneous system. Now if you perform mixing, you are basically trying to make them homogeneous, make the mixture homogeneous. You are trying to mix them in such a way that okay, in whatever spatial location that you look, you will find the volume, the mixed volume should be same in any of those differential spatial volume which you have considered for studying. So that is basically the homogenization. How well can you homogenize the mixture consisting of two or three immiscible phases? And the second aspect is the mass transfer. So mixing enhances mass transfer. So if your mass transfer is happening, so the particular process can be mass transfer limited, or it can be limited to the mixing. So if you perform the mixing well, then it just becomes the mass transfer limited step. Similar is the case for the heat transfer also, that if you want to transfer heat from one fluid to another, it may happen that you need to make an emulsion out of those immiscible phases to perform the heat transfer. And in the reaction kinetics also, so it might happen that the reaction on an overall reaction might be mixing limited, physically limited, but the reaction kinetics may be fast. So in such scenario, your job as a chemical engineer would be to perform mixing in best way possible. And then comes the scale up, that okay, not all systems scale up well, especially the systems where the mixing is involved. So in the micro reactor you might see that okay, mixing is happening very well between the two phases, but that the same cannot be true if you just increase the micro reactor scale from another order. So in such cases the mixing may fail. Or if you employ CSTR for your lab size prototype, so your one stirrer may work very well, but once you go from lab model to a plant model, your one stirrer will not suffice, and you might need to use much more sophisticated and many numbers of turbines and rotors to basically perform the same level of mixing what you were able to achieve in a laboratory scale equipment. So yeah, the mixing, you need to be very aware of the scale up issues with the mixing processes. The rate of reaction in a well mixed system is governed purely by the reaction kinetics. However, not all systems are well mixed. So the overall rate of reaction, as what I have just said, that the overall rate of reaction may be mass transfer limited, or reaction limited, or mixing physically limited. So your job here is that okay, how to make the system well mixed, so that the reaction kinetics may it just be limited to the reaction, the overall reaction rate might be limited to the reaction kinetics only, which then it becomes the process a natural process. So you cannot significantly alter the reaction kinetics itself, other than if you use enzymes or you go to the higher temperatures. But what you can do is you can minimize the resistances that are coming in between the pure reaction kinetics and no reaction. So that is the idea here, that you intensify the mixing. But not all systems are well mixed. So that same case, you might have a laboratory scale CSTR that might be performing well in a well mixed condition, but as soon as you scale it by just one single order, the whole system may go from well mixed to basically nothing. There will be no mixing happening. So you cannot play with the same rules once you scale up. So yeah, not all systems are well mixed. Now that we have defined what is mixing, now comes that why to learn about mixing phenomena. We have defined mixing, and we have said that the heart of the chemical engineering is the mixing, and we have also discussed the key aspects of the mixing operation. But why to learn about mixing? So the understanding of mixing is highly desired for the purpose of operation and designing of industrial scale reactor, because as I just discussed that okay, mixing does not scale well, the mixing operation does not scale well. So the understanding, if somebody has the understanding of mixing quite well, they will be able to design the industrial scale reactor much better. So that is why you need to understand or to learn about the mixing phenomena. Now similarly, the reaction progress, product distribution and yield are heavily governed by the mixing of the components in the mixture. So if the two phases, the reaction which might involve a multi-phase system, if they are not in a very good contact, if the mixing has not happened, if the surface area between them is very low, surface area to volume ratio is very low, the reaction will not happen and the reaction progress will not be high. So for that same reaction progress, because the reaction progress is very low, the product distribution with the entire reactant, the system would be very low, and thus the yield will be very highly affected and be very low. So that is why you need to learn about, or you must know about the mixing, that okay, how well can I contact them so that my reaction progress is high, product distribution is also very high, and the yield is also very high. So that is why you need to learn about the mixing phenomena. Now the large scale systems are difficult to be well mixed. So that I have just discussed now, that okay, they are not well mixed. Hence it is important to know the scale at which the variability will exist and the various mixing mechanisms that can reduce the scale up issues. So because the large systems are very difficult to be well mixed simultaneously by getting scaled up, so you need to know that okay, at what scale, at large scale, at the inconsistency, or the where there is variability, what is the size of those, or what is the scale of those variability, so that you can basically perform the mixing phenomena accurately to reduce the scale up issues. Now designing the mixing processes to yield a much shorter mixing time in comparison to the mean residence time of the reactants in the reaction vessel is of paramount importance for the optimal reactor performance. So the mixing process, so if you are going to design a novel reactor, it should be revolving around the designing of the mixing process to yield a much shorter mixing time. So if your residence time is very high and the mixing time is very low, so what happens is the reaction will happen in the whole residence time in which the component will be there inside the reactor. So if you do not perform mixing, so such species molecules will go unreacted, or they will not be able to experience the full potential of the residence time. So they will take up some time to first get mixed, then they will take up some time to perform the reaction. So your job must be to reduce the mixing time as soon as possible, so that the species inside the reactor are able to experience as more as possible of the residence time for the given reactor. So that is the goal here. So the reaction should go, it should not be mixing limited. Now the designing the mixing process to yield a much shorter mixing time in comparison to the mean residence time of the reactor in the reaction vessel is of paramount importance for the optimal reactor performance. So yeah, that same thing, that okay, to design the optimal reactor, you need to decrease the mixing time with the reaction time as compared to the reaction time. So your reaction time must be, it can be fast if the reaction has a very faster reaction kinetics, so then the reaction time will become very slow, but your job is to reduce the mixing time as much as possible. Now that now that we have established that okay, why, what is mixing, and why learning about the mixing is very important. Now, as we have just discussed that okay, your job is to reduce the mixing time. So the objective here is that how much can you reduce the mixing time, and what can you do to reduce the mixing time. So let us first discuss that okay, what are the factors on which the mixing time depends. The mixing time depends upon the column dimension and the design of the fluid distributor. Mixing time also depends upon the fluid flow rate, fluid properties, and the level of fluid mixture inside the column. So if your column dimension is a micro, so yeah, in the micro reactor, the column dimension is in the micro range. So the adjacent fluid particles or the multiphase of different phases will be quickly, will get quickly mixed. So as compared to the columns with larger dimensions. Now, in the case of the CSTR, the design of the fluid distributor could be helpful. Like, you will send the, you will send the gas through a gas sparger, so that the size of the nozzle that would generate the gas, if you could reduce the size, so what you would get is you would generate micro bubbles. So those micro bubbles can then help you to get very high interface area to perform mass transfer and to enhance the mass transfer operation in such cases. Or you can basically, if you can enhance the or improve the design of the atomizer that is used in the liquid gas system, where the gas is in the continuous phase and the liquid gets dispersed in the gaseous phase, there the size of the liquid droplets can be controlled by the design of the atomizer that is used to produce such micro droplets. So yeah, the design of the aerator unit in the CSTR or in the atomizer is a very important. And another thing is fluid flow rate. So what happens is multiphase flow is you will observe different flow regimes of multiphase flow. For example, in the two-phase gas liquid flow system, you will be able to observe four major flow regimes or flow distribution, where so those are annular flow, churn flow, slug flow, and bubbly flow. So these flow regimes or the flow distribution of the multiphase flow system actually depend upon the three factors. One is fluid flow rate, another is fluid properties, and another is the channel dimensions. So yeah, so actually these four, out of these four, the three of them actually comes from there only. That okay, if you can basically based upon the fluid flow rate, you will be able to observe different flow regimes, and each of the flow regimes have different mixing times based upon the types of hydrodynamics that they display. So fluid flow rate may plays a very important role in reducing the mixing time, and similarly fluid properties. So for a given flow rate, if you have a very high difference in the viscosities or the densities of the flow of the multiphase flow systems, so you might be able to you may observe flow stratification to happen, that is unwanted. You do not want that to happen. Just a minute. Okay, so yeah, these are the column dimensions. So the factors that determine the mixing time are the column dimensions, design of the fluid distributor, fluid flow rate, fluid properties, and the level of fluid mixture inside the column. So yeah, and this determines the overall rate of the reaction if the mixing times are much larger than the reaction time. So if you have a certain system where the reaction times are significantly smaller than the mixing times, what you are allowed to, so mixing times, so the reaction times you cannot generally change unless you use catalyst or you use high temperature or high pressure condition. So reaction times you cannot play around, but by changing the geometry, by changing the column dimension, but by changing the fluid flow rate, by changing the fluid properties, or by changing the level of fluid mixture inside the column, you can play around with the mixing times. And if the mixing times are very significantly larger than the reaction kinetics, then the overall rate of reaction becomes is determined by the mixing step. It becomes mixing step limited rate reaction. So the rate of reaction then becomes mixing step limited. So when the reaction is relatively fast as compared to the accomplished mixing rate, physical factors such as the sparger design, column diameter, rate of stirring, solvent viscosity, etc. contribute to determining the yield and selectivity of the overall process. So yeah, same thing again. If your reaction or the intrinsic reaction kinetics is quite fast as compared to the mixing step, then it is actually the mixing step that will determine the like the sparger design, column diameter, rate of stirring, and solvent viscosity is what will determine the overall reaction yield and selectivity. So that is why you need to learn about the mixing time, and your objective is to reduce the mixing time. Now, mixing phenomena is generally associated with turbulence because laminar flow is what we called as the diffusion limited flow regime. So laminar flows are diffusion limited. So where the convection and the mass and the heat transfer is just happens or occurs via diffusion only. So there is but the turbulent is what we associate with the mixing via convection. Now in the single phase turbulent flow system there are three different mixing scales. Now the mixing can happen in different scales. So you can perform the mixing, or basically if I would have to I would state in this manner that okay, if you want to study the mixing on an equipment like CSTR, so you can study the effect of mixing, like say you are changing the size of the stirrer, or you are changing the rate of which the stirrer rotates. So you change the RPM of the stirrer. So you are basically trying to note down the global mixing quantities. You take some input values and you take some output values at the reactor end. So there you are studying the global parameters. There you are studying the macro mixing. And then the mixing scales can be of different scales. So the scale at which the mixing that can be studied or that happens on a whole reactor basis is called as the macro mixing. And then comes the meso mixing and micro mixing. So the meso is somewhat the turbulent eddy is limited, that okay, where the vortex shedding is what is observed. So meso mixing is related to that and is referred to that, and micro mixing is where you will observe through the very small eddies like Kolmogorov scale or Bachelor scale eddies. So these three mixing scales are defined on the basis of their characteristic length scales and directly correlated with the turbulent energy dissipation rate or epsilon. So scale of operation is for the macro mixing, you will be able to observe, or the scale of operation for the macro mixing is global, like throughout the whole vessel vessel of choice. And for the meso mixing, the scale of operation is turbulent eddies, and for the micro mixing, the scale of operation is Kolmogorov or Bachelor scales. Now, as for the mode of operation, the macro mixing, the modes of operation for macro mixing happens in bulk convection, and the modes of operation for meso mixing is vortex shedding, and the modes of operation for micro mixing is the engulfment or deformation or diffusion of the liquid elements or the fluid elements. And the mechanism for the operation in case of macro mixing is turbulent diffusion or inertial convection, and same is for the meso mixing, also turbulent diffusion, inertial convection. And in case of micro mixing, it is the momentum diffusion or molecular diffusion. And the time scale of operation for macro mixing is that it is directly proportional to the your turbulent energy to the power inverse of the 1/3 epsilon. So here the epsilon is the turbulent energy dissipation rate. So in the mixing time, or the tau mt, the mt represents mixing times, is inversely proportional to the turbulent energy dissipation rate, and for the macro mixing it is minus 1/3, and it is for the same is for the meso mixing case also, it is inversely proportional by the order of 1/3, and in case of micro mixing it is also inversely proportional, but it is 1/2 or square root, inverse square root. So now coming into detailed discussion of each of those scales, the macro mixing involves mixing on the macroscopic scale. Okay. So macro mixing involves mixing on a macroscopic scale, which refers to the scale of the vessel or the reactor. The process is often referred to as the distributive mixing, and it is achieved by the bulk motion or convective transport of the liquid at the macroscopic scale, resulting in uniform spatial distribution of the fluid elements within the reactor volume. So in a continuous flow reactor, the macro mixing process directly influences the resonance time distribution of a feed stream introduced into the contents of the vessel. So the macro mixing time, so here what we refer to as macro mixing time in a mechanically stirred baffled tank is a function of the mean circulation time in the vessel. So you can say that the mean circulation time, and the vessel configured for optimized mixing is approximately about, the macro mixing time should be about the 3 times of the circulation time, and for a non-optimized system it is generally about the macro mixing time is about in the range of 5 times the mean circulation time. So the mean circulation time is generally expressed in terms of the impeller pumping capacity, or QC. Now in case of meso mixing, Now in case of meso mixing refers to the coarse scale dispersive mixing via turbulent eddies. It is typically characterized by the 2 different mechanisms, the turbulent dispersion. So it is characterized by 2 different mechanisms. The first is the turbulent dispersion of a fresh feed introduced to a vessel which mixes with its local surroundings. And second mechanism is the inertial convective breakup of the large eddies that are larger than the Kolmogorov length scale. So the characteristic time scale associated with the turbulent dispersion can be defined by the that depending upon the radius of the feed pipe with respect to the characteristic length scale for the dispersion. So it is a function of the characteristic time scale associated with the turbulent dissipation in respect to the mesoscale mixing depends upon the pipe radius and the characteristic length scale of dispersion. So the inertial convective mesomixing time scale is that same. It is also a function of the pipe radius and the characteristic length scale of dispersion. Now in case of the micromixing represents the final stage of the turbulent mixing processes, which proceeds at a much finer length scales than the macro and mesomixing, referred to as the Kolmogorov-Batchelor length scale. Now the Kolmogorov length scale represents the smallest scale of the turbulence before the viscosity effects start to dominate, and the Batchelor length scale represents the smallest scales of the fluctuation prior to the molecular diffusion. So now Kolmogorov and Batchelor length scales, so they are basically related, Batchelor length scale is equal to the Kolmogorov length scale divided by the square root of Schmidt number. Now the Schmidt number for liquids is typically of order of the 10 to the power minus 3. So taking a square root of that will be a very large number, and taking the length scale of Batchelor length scale into Kolmogorov length scale to be very, very small. So what happens is, if you divide by such a very large number, you will observe that the Batchelor length scale for liquids is specifically for liquids is very, very low than the Kolmogorov length scale. So for the aqueous solution, for an example, aqueous solution in the turbulent regime, the Kolmogorov's length scale is of order of 10 to 30 millimeters. Now that we have discussed about the different types of mixing and different scales of mixing, now let us come to the greener chemical processes. In the previous session we have discussed what is the green chemistry, and green chemistry is one of the important strategical movement for the process intensification in chemical industry, and its definition follows as the utilization of the set of principles that reduces or eliminates the use or generation of hazardous substances in the design, manufacture and application of chemical products. So an ideal process is the one in which the byproducts are reduced or eliminated altogether at the reaction stage, rather than focusing on removing them after they are formed, a concept known as the waste minimization at the source. So focus on do not focus on the removing of the waste product after they have formed. So the whole the idiom or the whole line of prevention is better than the cure is summarized in this one. This entire line summarizes as the prevention is better than the cure, because the ideal process is the one in which the byproducts are reduced or eliminated altogether at the reaction stage itself, rather than removing them after they are formed, which is the whole crux of the movement known as the waste minimization at source itself. Now this promotes the development of the intensified reactor technologies for the greener processing. Now the successful implementation of the greener chemical processes relies on, the development of more efficient catalyst for synthetic chemistry and the development of the reactor and separation technologies in safe, cost-effective and energy-efficient manner. So yeah, that will determine your successful implementation of the greener chemical processes. Now that was just a brief about the greener chemical processes. Now let us discuss about that CSTR. Again, the concept of mixing time will come. But yeah, let us now discuss in terms of the CSTR's residence time distribution. So the CSTR is generally, conventional in conventional chemical process industries. CSTRs were used, but these are not favored as of now, and they should not be favored even in the future. Also, yeah, they should be favored, but the better and better types of reactors are coming around. So we should go beyond, and as a chemical engineers, we should design the systems thinking beyond the CSTRs. So, because the CSTR residence time distribution is generally not desirable, because much of the material in the reactor will spend too long in the reactor. And the main problem with this is that it allows for the competing reaction to become much more significant, because so some of the material will spend too long. And then the third problem is that some of the material or the much of the material will be in the reactor for less than the desired residence time. So if you see the residence time curve for a CSTR, there is, you will notice the the presence of dead zones, and you will also see the presence of dead zones, but because the residence time distribution graph will not completely go zero. So there will be just a long tail that will go in the x-axis. So that tail is due to the presence of the dead zones. So the tracer particle will still be staying on the CSTR where the dead zones occur. So they will not come out of the CSTR. So yeah, that because of those tracer particles that are staying too long, or the species that stays too long in the reactor, it become overcooked, or basically it will allow for the side reactions to happen also. Now on the other flip side of that is, you will also see in the CSTR's RTD, you will also be able to observe the phenomena of bypassing happening. So what happens is, as soon as the tracer particle gets into the CSTR, instead of getting mixed, they quickly get passed away. So those fraction of the tracer particle that quickly get passed away are known as the bypass tracer particles. And this for the same when this happens when the same happens for the species of interest, or the chemical species which are going to undergo a chemical reaction, and when they are not able to completely get well mixed with the system, so they will get bypassed without even having a chance to react. So therefore they will not be able to reach the desired level of conversion. Thus the CSTR can lead to the increased byproduct formation and unsatisfactory conversion. So the increased byproduct formation is a very consequence of the dead zones, presence of dead zones, and the unsatisfactory conversion is the result of the bypassing phenomena of the CSTR. So that's why we need to go and think beyond the CSTR itself. Now let us discuss briefly. So last time also we have discussed about the intensification using centrifugal fields, using electrostatic field, and using ultrasonic waves, and using of microwaves. So again, let us discuss about the intensification by electrostatic fields. So the large interfacial areas formed due to the small droplet formation under the electric field. So the electric field, when you apply electrostatic field, what happens is, Okay. So yeah, electrostatic field, when electric fields are applied, so the small droplets, micro droplet formation happens that leads to large interfacial area, and this allows for the highly stable emulsification to happen, and hence so this when the when the stable emulsions are formed, so you will be able to keep that emulsified. So the more stabler the particular emulsified system is, the the longer it will stay as that system, stable system, and therefore it will enhance the overall rate of reaction in immiscible liquid systems. Now, for an example, in the enzymatic hydrolysis of triglyceride esters to yield free fatty acids and glycerol, the electrostatic fields are used to intensify the dispersion of the aqueous phase into the oil substrate by creating large interfacial areas between the reacting species. Thus, they can enhance the overall rate of reaction at relatively modest temperature and pressures. So that's why electrostatic fields can be used to perform process intensification. Now, process intensification by microwave irradiation. So again, in the previous session also we have discussed that okay, microwaves can be used to perform process intensification. The microwave assisted processing, where the microwave exposure result not only in higher rates of reaction than the conventional heating method, but also in better product quality through improved selectivity. So what happens in the microwave is you will be able to perform volumetric heating. So in the other sorts of conventional heaters, what you will do is, like in the CSTR, you will use immersion heating rods, or you will heat the entire CSTR from below, or you will you will provide heat by CSTR walls. But then it is not a volumetric heating; it is a surface-based phenomena. But in the microwave heating, or when you use microwave assisted processing, so microwaves perform volumetric heating. So the small scale batch and continuous reactor system where the microwave irradiation capabilities are commercially available. And the examples include the hydration of nitriles, isomerization reaction, reduction reaction, coupling reaction, condensation reaction, multi-component reaction. So these are some of the systems that can be intensified using the microwave radiation processes. So yeah, these were the process intensification. So this was the second live session, and today we have discussed that okay, process intensification, the multi-phase flow system. So we first started with the discussing that okay, what are the multi-phase flow system, and then we have discussed in details that okay, what are the different types of multi-phase flow system, like two-phase system, three-phase system, four-phase system, and what are the examples of such multi-phase systems. And then we have discussed that okay, the reactive distillation system and multi-phase microreactor systems. And then we have discussed the heart of the chemical engineering, that is what is mixing, and mixing phenomena in chemical engineering. So what is mixing, and then we have discussed about that okay, why to learn about the mixing phenomena, and then we have discussed then we have discussed okay, why to learn about mixing phenomena. Then we have discussed that okay, what are the different what are the different levels, scales of mixing. So then we have discussed the objective is to reduce the mixing time, and then what are the different scales of mixing, that okay, macro mixing, meso mixing, micro mixing, and the scale of operation, modes of operation, mechanism of operation, and time scale of macro mixing, meso mixing, and micro mixing. And then we have individually discussed all of the three lengths, and then we have discussed about the Kolmogorov and Bachelor length scales, and then we have briefly gone over the green chemical processes, and then we have discussed that okay, why the CSTR is generally not desirable in today's age because of their RTD. So if you see as any RTD study of a flow inside CSTR, you would realize that okay, there are presence of dead zone and the bypassing happens. So that is why CSTRs are not very desirable. and intensification by electrostatic fields, then we have discussed, and then we have discussed intensification by the microwaves. So this concludes the live session for this week, and let us meet next week. So yeah, thank you.